Okay, we'll go ahead and get started. Thanks everyone for attending. Just a reminder for those, if you haven't done so already, to check in through the campus groups link. There's a QR code there that Sierra's holding up. You can check in at the end as well. But just be sure to check in. That helps us keep report the numbers so that we can keep getting the food. And it's my pleasure to introduce Professor Molnar from the Micron School of Materials Science, who's going to introduce today's speaker. So I'll turn it over to you.
Thank you. I'm Peter Molnar, and I have the pleasure to introduce our guest speaker today. Who in this room recognizes and knows Dr. Markus Chmielus? So there's still a few here, yeah, and so it is my great pleasure, and it's a highlight of this month to introduce him. It definitely is a highlight of my career to have been working with him over the last now 20 years. Dr. Chmielus is a professor at the University of Pittsburgh, where he's also the director of program director for material science and engineering in the Department of Mechanical Engineering and Material Science and Engineering. He joined my research group after completing a master's at the Master of Aerospace Engineering, I believe it was, at the University of Stuttgart in Germany. He also got a degree at the same time, kind of as a side geek, at the conservatory as an organist and on the classical organ, church organ. When he completed a master's here in our program, Material Science and Engineering, and then continued with a PhD. And those who have been here long enough know that at that time we did not have a PhD program here on our campus in material science. So he got his degree or his PhD from the Technical University in Berlin. While he did at least half of the work here, right? We spent every 2 months here and then 2 months there and back and forth. So he was absolutely the frequent flyer of our program. I don't know if anybody got even close since then. When he graduated, he had his name on 12 publications, including at least half of them as first author, including a paper in Nature Materials, which by now has garnered about 450 citations. He moved on from here to join Cornell University as a postdoc for 3 years, from 2010 to 13. And from there he got, after that, joined the University of Pittsburgh, where he mostly pursues additive manufacturing of various materials, metals, ceramics, even clay. He's one of those faculty now who establishes kind of a pipeline between Boise State and the University of Pittsburgh. I think they have now 3 faculty from our College of Engineering, including 2 that have been working in my laboratory. So I think he met also with a few students this afternoon. And so if you had some opportunity to talk to him about what opportunities are over there, he is here also to help you with that. And with that, I'll hand it over to Dr. Markus Chmielus.
Thank you so much, Peter. That was a great introduction. I can't even remember that, so I'm impressed. Thank you. Welcome everybody to the seminar. I'm very excited to be here. It's great to see what happened at Boise State. I really love this building. It's fantastic. This room is great too. And I love that there's so much energy here. When I was in the high bay, where I walked through when I was a student here, and there was so much student activity. So I really love that. And I think you are here in a great place, right? Unfortunately, not as much snow as I remember from the time that I was here. So today I'm talking about binder jet additive manufacturing of structural and functional materials. And this presentation is based on all the work of my graduate students that have been there or are currently now in the lab. And obviously, this work would have not been possible without our collaborators. Here, Peter is a great collaborator, but also others in Europe and throughout the US. And also, I want to acknowledge our funding that comes from Air Force Research Lab, Naval Nuclear Labs, NSF, and so on. and then also many companies that actually work with us on Binder Jet 3D printing. Okay, Pittsburgh. You may not know too much about it. You probably know it is a steel city, and it looks exactly like this, right? Super dark, all dirty and everything. It is actually not like that anymore, right? While Pittsburgh was the main producer of steel, glass, and coke of the United States, it is now a hub for medical science, artificial intelligence, and so on. The University of Pittsburgh was founded actually the same year as the US Constitution was signed, so it's pretty old. We have now 34,000 students on 4 campuses. And one thing you do not know, and I always have to look this up when I give a talk, is we are actually the 12th highest university in the United States when it comes to federal research expenditure. So we spend around $900 million per year on federal funding, right? Most of this is on medical research. So we have a huge medical school. And so the engineering school is a little bit in the shadow of the medical school, which is sometimes not bad, right? We also have then 300 million probably in funds from either the state or from foundations or other organizations. Okay, so today in my talk, I will give you a brief overview of Binder Jet 3D printing. And I'm splitting that talk up a little bit in structural materials. Then I will also talk about functional materials. And finally, I will talk about a project that came out of experiences that we had with binder jetting and some fairly recent occurrences in this country and in the world. And that is on porous binder jetted structures. So what is binder jet 3D printing, or short binder jetting, right? When you look at the landscape of additive manufacturing, then how I like to usually structure and categorize additive manufacturing is, do we have a method that can print metal parts directly, or do these methods only print them indirectly? For example, you make a shape and then pour metal in it or something like that, right? So when you look at the methods of additive manufacturing, you see VAT polymerization, which is fairly common. You can actually buy now these printers for like $1,000 or something like that. There's material jetting, which you have here in the department. There's material extrusion, which is probably the most common additive manufacturing method for amateurs, right? And that is FDM printers. You can buy them for $150. And then on the other side, we have direct energy deposition, we have powder bed fusion, we have sheet lamination. That are all methods that can actually print or additively manufacture metal parts. And then there's the odd one in the middle, which is binder jetting. And in binder jetting, you can actually print metal parts directly, or you can print sand molds and then use them for sand casting. That is actually the biggest business for binder jetting, is printing sand casts. And companies that do casting, metal casting, actually were able to reduce their development time for parts from a year or 2 per part redesign to several weeks, right? So it's a huge, huge impact on the metal casting industry. So how does binder jetting actually work? What we're doing here is we are laying down a layer of metal powder. We roll it, make it flat. And then in the next step, we are bringing over a inkjet cartridge that you can see here. It's basically like your inkjet printer, but instead of ink, we are printing a glue, right? A binder that is binding particles together in very specific regions that are defined on a 3D model. And then we are drying this binder briefly to evaporate either a solvent or water, depending on what binder you have. And then after this, you consolidate, you cure the binder and are able to take out your part, and then need to do a high temperature heat treatment. This high temperature heat treatment is needed because after printing and curing, we have a part that's very chalk-like. So if you have this in your hands, you can actually rub off the powder. It is fairly stable. You can drop it from shallow heights. but the problem is it will just break if you put pressure on it, right? So in the high temperature heat treatment, we are applying a temperature that is fairly close to melting point. We densify our material. Since there's a lot of porosity in the S-printed part, it actually shrinks, right? And as I already mentioned, we need to be very close to the liquidus line here, right, to densify quite a bit. But how does this densification actually work? So if we're looking at our sintering process, initially we have just powder particles that are next to each other. They are touching a little bit, right? During the sintering process, we have first a coarsening step where we have necking starting between those powder particles. And then we have our, through surface diffusion and evaporation condensation. And then we have the densification step as well, where we have volume diffusion and grain boundary fusion as the mechanisms of densification. So why would we even do binder jet 3D printing? I mean, you need to do this weird sintering process. That's another step, right? Very time consuming. But on the other hand, you can print extremely fast. If you know laser powder bed fusion, you have like one laser or maybe two lasers. It takes a minute or two for each layer to actually print. Here, modern systems can actually do the entire single layer in one swoop. So you have powder deposition, directly behind it printing, and directly behind it drying, right? So the process is about 100 times to 200 times faster than laser powder bed fusion. We have no residual stresses during printing because there's no melting, right? So that is really, really good, especially for materials that don't weld well, right? So if you have materials that don't weld, binder jetting is really something for you. But on the other hand, you need the post-processing, right? You need sintering for densification. But in powder metallurgy, and in Pennsylvania, there's a large amount of powder metallurgy companies out there. You need to do this as well, right? So this process is actually well understood in the industry, how to densify, how to sinter things from a powder. And since we have a powder bed throughout the build, we can actually build really complex structures with overhanging parts, flat parts over the entire layer, right? And they will not sag down or anything during printing, like in laser powder bed fusion, for example. So there's a lot that needs to be still considered. Doing binder jet 3D printing, we have an interaction between the powder particles and the binder that you're using to glue these powder particles together. And if you look here at this little video that I took, you see this is basically a binder, right? And here we have different cellulose that you can think of as different powders. Okay. What you can see is the binder is seeping into one of these much more than in the other two. And that is the same in actually powder, right? Depending on what kind of powder you have, depending what kind of binder you have, the powder-binder interaction can be very different. Right? So you need to understand how this interaction actually takes place, how far your binder actually leaks in. Will you have nice shapes or will you have binder bleeding in your parts? You need to consider powder flowability, because if you have very sticky powder, like a very fine sugar, right, powdered sugar, then it sticks. If you have granular sugar, then it flows actually really well, right? So in binder jetting, it is always better to have flowing powder. You can also get around with non-flowing powder, but that's a different story. You need to look into what is the shape of your powders. Does the powder have porosity? And then you need to think about, okay, doing printing, how thick are my layers, right? With respect to maybe the powder size. How fast do I spread the powder? How do I tap it? Do I tap it, right? There's a lot of considerations during the printing aspect as well. So what we need to look at, what we learned now so far is we need to consider the raw material, powder and binder. How do they interact? We need to print and check how do my print parameters affect my printed parts. And then finally, we need to do post-processing, which means sintering and densification. So now that you're all expert on binder jet 3D printing, I will talk a little bit about structural materials. What do structural materials have in common? What do they need to be usually? Anybody wants to chime in? Structural materials, what do they need to be? They need to be very strong, right? So, and in order for be very strong, they need to be fairly dense as well, right? So for structural materials, that is usually the goal, right? We want to have very dense materials. So we started with Binder Jet 3D printing now over 10 years ago. And the first project that we had was actually looking at, can we use cheaper powder than gas atomized powder? Gas atomized powder is really nice, spherical, flows super well, but it's very expensive. Water atomized powder, not so good, right? It's not spherical, doesn't flow very well, has contamination and so on. But for industry, it's very interesting because it's much cheaper. So we wanted to figure out what's actually the difference between the two, and can we use them in binder jet printing independently? So we did a sintering study. You see here, we heated our materials up to the same temperatures, right? And then looked at how do they actually densify. So we saw that in gas atomized powder, which is the spherical one, we see really nice densification up to nearly 100%. In water atomized powders, we didn't see that. We only got to like 95 or something like that. And what was interesting to me at the time, because I was extremely naive, so what we saw is that this translates directly into mechanical properties, right? So at the points where we have highest density, that's where we had the best mechanical properties as well. And what we also saw is, even though we might not be full dense, we can still, after sintering, age our material to change the properties of these metals, right? We can make them a little bit harder, increase UTS, which would result in less ductility. But still, we can modify through aging after sintering as well. Now we wanted to understand what is actually happening in these materials. And what we saw fairly quickly by micrographs from cross-sections of these structures is that gas atomized powder has actually this really fine pore microstructure at low temperatures. Then we have coarsening of the pores, and then we have pore elimination. In water atomized powder, that didn't happen at all. We had basically the same pore structure throughout, but what we also saw is that there were a lot of secondary phases. These were carbides and oxides that decorated the grain boundaries, right? And those slowed down the densification process and also the pore elimination. If we, as I mentioned, we were very naive in the beginning times, and so we just followed the printing parameters that the binder jet printer manufacturer gave us for these materials. That's usually a bad idea, okay? Don't do that. It's a good first step, but then you need to actually figure it out. So now what we did next is we looked at how do actually the print parameters affect the green density, because we want to get this as high as possible. What we saw is that for these two different powders, water atomized and gas atomized powders, the main effects of the print parameters, so basically what affects the green density the most, are actually very different. So for water atomized powder, it was just binder saturation. That had a big effect, the other ones really not much. For gas atomized powder was the roller traverse speeds, so how fast you're spreading your powder, and then how fast you're compressing your powder with the roller. Right? So that was very interesting. So we optimized this here to the highest density, and then we just modified binder saturation for both. And what we can see here is actually really nice structures in the middle, so around 80, 100% binder saturation. Then we have here binder bleeding, and at the bottom, the lowest binder saturation resulted in delamination. So the parts were just too chalk-like, right? They were not even chalk-like anymore, right? They just delaminated. So here we looked at the density, green density, so as printed density, and then also density after sintering. And what we could see right away is that the green density really translates into the sintered density. So the higher your green density, the higher your sintered density. And then, as we saw before, sintered density also results into the mechanical properties. So whenever our green density was highest, sintered density was highest, mechanical properties were the highest, right? So what you can learn here from this is the better you print your material, the better your final mechanical behavior, right? So we wanted to learn more. Now we employed hundreds and hundreds of undergraduate students, right, to cut and polish tens of thousands of samples. No, not that many, but many, many samples for different size distributions of powder, different temperatures that we sintered at, and different times that we sintered at. Because what we want to learn here is what is actually the densification or sintering mechanism that is taking place during sintering, right? And so with these different sintering times and temperatures, we could figure out that we actually have at the highest temperature grain boundary diffusion. At the intermediate temperature, we have volume diffusion and grain boundary diffusion. And at the lowest temperature, we have a situation where probably the defects are affecting the densification so much that there's no clear diffusion process or densification process present. So you saw on these previous pictures, if you looked really closely, that there were lines in some of them, right? So these are print defects. If you have a powder, especially if you have a light powder, smaller powder size, maybe lower density powder, then you imprint defects each layer, right? And we wanted to see, is this actually something that is real, or is this just a defect maybe on the 2D microstructure? So we did microcomputed tomography and saw that no, this is actually real. It's throughout the structure, and this can be a problem, right? If we need to print small particle powder or light powder, then we need to fix this. So one thing that we did is we looked into using supersolidus liquid phase sintering. So just going a tick into the region where we have a liquid phase forming, okay? And we don't do this very long. We just do this for a brief moment to form this liquid. The liquid is formed on the particles, is basically coating the particles and then helping the densification process quite a bit. And by doing so, we can actually reach, so this is the solid state sintering, we can actually reach with supersolid liquid phase sintering for half an hour, really dense structures, right, in 3D. So that's a really cool thing because now we basically have a mechanism to repair large defects, right, without distorting the part. Because now we need to be very careful. If we go into liquid phase sintering, we just have a blob afterwards, right? It doesn't matter what you print. It's literally just a drop, right? We did this many times when we went a little bit too high. But yeah, be careful, find the right temperature, and you can actually repair defects in your printed structures. Okay, so how can binder jetting be a successful additive manufacturing technique? Well, we need to understand the feedstock materials compatibility and interaction, so powder and binder. We need to optimize the as printed green density because that translates into the sinter density, right? And the microstructure. And then we need to also, and we didn't talk about that, optimize the design as well. Because if you have a ginormous part that is all solid, it's very difficult to get the binder out, right, from the center. So you need to design for binder jetting, basically. Okay. Next topic. Okay, we're switching a little bit around, and we are going into an area that has quite some tradition here at Boise State, and that is magnetic shape memory alloys. So this is something I worked on when I came here, and Peter Milner is one of the main researchers in this field. And so when I started at Pitt, I was wondering, well, how can I actually use my knowledge that I got here at Boise State and combine this with additive manufacturing, right? As a quick introduction, magnetic shape memory alloys are actually really cool materials. They're solid and they deform up to 12% in a single crystalline state when you apply magnetic field or change that magnetic field, right? What is really cool about them is that they perform really fast because they don't need a phase transformation. You don't need to heat and cool them, right? Like shape memory alloys. As polycrystalline materials, they're terrible, right? If you just cast a nickel manganese gallium magnetic shape memory alloy, they will probably not do anything. So you either need very large grains compared to the size of your part, or you need to add porosity and disconnect those grains, right? So that each grain can act as a single crystal by itself. Another problem here is that the functionality is really, really influenced by the composition. And it is also really influenced by defects, right? Do you have a rough surface, right? Do you have some other phase in your structure? So all of this make these materials quite difficult to work with, right? But where there's difficulty, there's always an opportunity, right? So for additive manufacturing, what I really looked at was designing multi-scale porosity, right? I looked at, can we actually print very complex shapes, because these materials are fairly brittle. And so when you want to machine them, they can break very easily. Also, for certain additive manufacturing techniques, you can manufacture gradient or equal compositions and therefore functionality. So that could be for direct energy deposition, for example. We can potentially grow epitextually. So we can grow single crystals using direct energy deposition. And we can connect our structure or functional structure here to the support structure so that something like this does not happen, right? That our functional materials flies away. Binder jetting, though, on the other hand, is really useful for this porosity, complex shape, and what is really important for us is the controlled composition, microstructure, and properties. And that's what I will talk today about, is binder jetting of these materials. So in my lab, we are making powder, we are characterizing it, potentially post-processing it. We print AM samples, then characterize them, potentially post-process them, and do functional testing, right? Yeah, that's a cool Pac-Man, right? Was it one of your samples? I'm not sure. So that actually broke while we ran the test, and it looked really cool. A little Pac-Man, love that one. And so our first test was what kind of sintering atmosphere actually works with nickel manganese gallium. So I worked on single crystals, and when we manufactured them, we had a lot of compositional problems with them, and so I was aware that there is can be some issues. So we looked at vacuum sintering, and we saw very quickly vacuum sintering does not work at the surfaces. We have really changes in composition, and those will then actually result in dramatically changed functionality. So here on the right side, you see differential scanning calorimetry graphs, which show you phase transformations, for example. And in vacuum sintered, you don't see any of them, right? This here is what you should normally see, like martensite phase transformations, right? Here you see magnetic functionality, and that's also completely gone for our vacuum sintered material. But if we backfill with argon, our structure looks actually pretty good. We have twins, which indicate martensites. We also see phase transformations and really good magnetic behavior, right? So atmosphere plays a big role in these materials. Now we wanted to figure out sintering mechanisms again, right? See, how can we actually optimize the pore size so that our grains are disconnected, make really large grains at the same time, right? And for that, we again had a lot of undergraduate students in our lab that cut and polished a lot of samples. And what we found is fairly obvious: with increasing temperature, we are increasing density and grain growth. With increasing time of sintering, we are increasing density and grain growth, right? But one interesting thing was, with increasing time, we saw pore shrinkage. So the pores got smaller to some point, and then the pores coalesced again and grew actually. But we also eliminated some pores. So we can use this graph to actually identify the optimum pore size, optimum grain size for these structures. Here you can see we reached actually around 95% density for these materials. And we use this graph that shows you now for different sintering temperatures and different sintering times, the density of these materials. We can use this to actually, again, identify densification mechanisms. So when we go to 1070, which is this line here, the slope in this volume rate versus inverse grain intercept shows you or gives you an indication of the densification mechanism. For 1070, the lowest temperature, it's again very difficult to identify. Probably we have an interplay of coarsening and densification mechanisms, and we also have a lot of defects that haven't been repaired at this temperature. For 1080, we do see volume diffusion. This slope here is a 3, which indicates volume diffusion. So we have a faster densification rate, slower grain growth. And for high temperatures, we get grain boundary diffusion, which is slower densification rate, faster grain growth, and significant pore rounding. So instead of elongated pores, we see actually round pores. So what was really cool about this is all the functional properties that we measured before, they stayed the same, except for 1100 degrees C. Can anybody imagine why that one was different? 1100 C. Anybody wants to take a guess? Uh-oh. Uh-oh. The temperature is too high. We melted our part, okay? So we had a lot of compositional changes there, a lot of evaporation, basically, right? So we changed our composition, basically. That's why this was not so good. But the cool thing is all the other temperatures, all the other times resulted in the same functional magnetic and phase transformation, right, properties. And that's great because now we can really just focus on our pore microstructure. So are we done with binder jetting? So we understand the sintering kinetics a little bit better. But we still have oxides. So you couldn't really see it, right? But even in argon backfilled sintering, we still have oxide layers, and they're detrimental to functionality. Also, the grains are disconnected, but they are still randomly oriented. So we want to get as close to a single crystal as possible, right, if we can, because that would increase functionality. If you remember, magnetic shape memory alloys function best as single crystals. And then we haven't really taken advantage of additive manufacturing really here too much, right? We could just compact these materials as well. So one of my students, the next 3 slides took 5 years, right? So just mentioning that. So this was an oxidation study because one of my students really wanted to figure out what is actually going on in these materials, right? And so we found that we are forming manganese oxides in various forms. There will be 2 papers coming out this year where you can read all about it, but I just don't have enough time today to talk about it. What was really cool though is what she also figured out by just trying to figure out what kind of oxides are forming. She used a very classic method of a Rhines pack that creates an oxygen partial pressure in a encapsulation tube to actually eliminate oxidation completely, right? So this is a really cool result. So when you look here at binder in vacuum, right, versus binder in manganese oxide, there is no oxygen, or very, very little, right? So this is amazing. Now we have a mechanism that we can use to sinter nickel, manganese, gallium without any oxidation, with binder present, right? That's really cool because we eliminate now contamination. We have really cool pore microstructure. We know how we can modify this, and we keep our functional properties, magnetic properties, and phase transformations constant over these times and temperatures. So very cool results. As I said, 5 years, right? Just 2 slides. What we then also worked on is, well, we want to do this a little bit better, right? So we are building our own printers, especially for this. And we use magnetic field assisted binder jet additive manufacturing to actually orient our powder during printing, right? So what we can see is, depending on the orientation of the printed structure, we actually have maximum direction, which is the aligned direction, versus a minimum, right, for these materials. So we can align our grains in a polycrystalline material that is printed via a magnetic field assisted binder jet 3D printing. And then we can also print multi-materials in binder jetting with our custom printers. And so those are super useful if you want to combine certain behaviors of functional materials. Maybe you want to have a material that deforms on one side and is cooled on the other side, right? Maybe a magnetocaloric material on one side, a magnetic shape memory alloy on the other side. Or maybe you have a structural material on one side and the functional on the other side, right? So this is really cool, and we're working on all of this currently as well. Okay, how much time do I have left? 10 minutes. Okay, now we're coming to another cool project. So here we are now taking advantage of the disadvantages of binder jet printing, right? So if you have something bad, just make it a good thing, right? So the motivation for this was actually COVID-19, okay? So during COVID-19, you all remember that you had to clear the labs, run away, stay at home, right? And during this time, directly the first week in, I got a call from a friend of mine who works at the University of Pittsburgh Medical Center. And she was saying, we are out of face shields. We don't have disinfectants anymore. We don't have masks, right? And we're running through them. We're getting them in and they're gone within a day, right? So can you help us? So what we did in the engineering school is we just received 20 small FDM printers just the week before the shutdown, right? By chance, including tons of material. So what we started doing is we built actually face shields, holder for face shields for them. And we started to do all kinds of other things for our local hospitals. And what we then also thought about, well, there's a lot of companies around the area that might want to help too. And they actually did want to help. So local hospitals needed help, companies wanted help. We were in the middle of this, right? Because everybody contacted the universities. So we formed a collaboration with several companies in the area, powder manufacturers, additive manufacturing companies, and us. And we started to work on a project that had tons of energy and tons of naivety, right? So we were really excited and had no idea what we're doing. So that's always a great combination. So our idea was to build a filter that is made out of metal that you don't throw away, that is self-sterilizing. So we're using copper here. We're using high surface area material by doing all these channels that is thin, and we make them porous because binder jetting is porous already, right? So we don't need to worry about densification anymore. So we now keep it porous. And then once a droplet with COVID-19 is actually hitting copper, it would die within 10, 15 minutes, right? So copper is very antiviral, antibacterial. And so the cool thing is now a clinician or a nurse can wear these, right? Put them on their desk in the night, and the next morning it's sterile again, right? They don't need to do anything. They can just reuse it again. That was the idea. Okay. So again, tons of energy, tons of expertise. We knew all about it. We were like super enthusiastic, right? And so after a year of doing this, we came up with prototype devices that looked pretty scary, but still functional. And we saw that depending on how our design is, actually you can start breathing through these metal structures, right? But they were still not good enough. They were very heavy, very large, right? So that's a big problem. And if you ever work with a company, after 1-2 years, they do lose interest, right? If it doesn't work right away. And so we continued working with a few on projects together, but we were the ones who stuck around, right? Trying to figure this out because we thought like, this is solvable, right? This is a problem we can solve. Okay. So first we need to figure out how can we actually print copper. Copper oxidizes so easily, right? It is unbearable. Even just curing the material to cure the binder already oxidized the entire structure. So we took advantage of that. Again, taking advantage of the bad thing, right? So we were debinding under air, actually getting this out, completely oxidizing the material, but then using hydrogen to actually densify. So hydrogen can get rid of the oxide on the surface, and we can fully densify these copper structures by just using a little bit of hydrogen, 5%. In industry, that is actually done, but under 100% hydrogen, which we were a little bit wary of, right? So we didn't want to do that, but 5% is actually fine. We also looked at the binder and figured out we used the wrong binder from the start, right? So a different binder resulted in much less carbon and oxygen contamination. And then we also thought, well, the gas atomized powder, again, is very expensive. So let's work with some local manufacturers of powder and actually get super cheap powder. These powders here are actually machine powder. They're basically chips coming from a lathe, right? So super chunky powder. And we tried all kinds of aspect ratios between it, from super chunky to spherical. We also added space holders to our materials, so to add extra space, extra porosity. And then we looked at how does actually the amount of space holders affect the microstructure for each of these different powders that we got. So you see, we got a large variety of microstructures, right? And that will result in a large variety of pressure drops, of capture efficiency, so how much particles are actually getting captured, and then the quality of these filters. And we are right now testing all of these. So these are the first results. Sam just sent me these results on last week, no, this week actually, it's Friday, so this week. As you can see here, we are just going to, for capture efficiency, just to 40%, also for the quality factor. But what you can see, these are materials that don't have extra space holder in it, just sintered, right? Different densities. We are getting very close to N95 material for pressure drop. Pressure drop is how easy is it to breathe through these materials, right? So we're nearly getting there, while capture efficiency is pretty high, right? So we are in these more dense materials, we're very, very high, better than N95 material. Quality factor is not that good yet, at least not for these materials, because we haven't tested higher porosities yet, and we haven't tested the space holder materials yet as well, right? But this is very good data, and Sam, if you see this on YouTube, I hope it only gets better, right? Okay, so we reach pressure drops and capture efficiencies that are comparable to N95 masks. The quality factor is still a little bit lower, but hopefully with the higher porosity materials, we actually see exactly what we need to have, right? Okay, you're nearly done, okay? I hope I showed you that binder jetting is really a cool method of additive manufacturing, where you can actually look at the powder, sintering, printing, and actually come up with a structure that is what you need, right? For a porous project, for a solid project, for functional materials. And then I hope I also showed you that when you use advanced methods, you can even go further than that, right? You can now use magnetic fields, you can do multi-material printing, you can look in 3D how those structures look like, and you can repair defects as well. So really, really cool things, right? And I want to say thank you, but do you know what Pittsburgh all did? First drive-in gas station, first commercial radio station, train air brakes, AC transformers. I need to run really fast because I'm over time. First Ferris wheel, that was actually Butler. First commercial video call, the Big Mac. Did you know that? That was actually a McDonald's subsidy in Pittsburgh because there was competition from a Pittsburgh fast food chain that had something like a Pittsburgh Big Mac. CPR and DOL and EMTs, Pittsburgh. Polio vaccine saved tens of millions of people. Then the Jeep, actually also not Pittsburgh, outside of Pittsburgh, but I count that. Then the first snap top cans, also Pittsburgh. First emoji, very important, right? And ANSYS, does anybody use ANSYS for modeling? It's actually our namesake for the Swanson School of Engineering. John Swanson is the founder of ANSYS. Thank you so much for your attention. I hope you had some fun.
Thank you for the wonderful presentation. Now the floor is open for questions from the audience.
Thank you, Dr. Chmielus. Now, we were talking earlier about porosity and pores. I'm curious about how small you can get the pores, and is it related to the size of the powder, or is it controllable by sintering?
That's a great question. So you sometimes have remaining porosity from the powder porosity itself, right? Let's take this aside. You can control the porosity by some degree. Sometimes if it's very large, it's very difficult to get rid of, right? And then you need to do hot isostatic pressing. I think we mentioned that. We talked about that as well. So sometimes sintering is not enough to get rid of porosity, and sometimes you need to do a little bit more. But in between the super porous and non-porous at all, you can dial it in. It just takes a little bit, right? Takes some effort. Yeah.
Hi, Markus. That was fun.
Hey.
So I don't know if it's too early to ask this question. Have you done like a cost comparison for your filters? 'Cause I'm imagining the copper filters cost a lot more to produce, but then you could reuse them, so that's in their favor.
Yeah.
Have you done an analysis, or is it
So
early?
there was actually a company who did the analysis for us because they approached us and if we can do this for them. We were too early in the project, right? Where we were like, we're not quite sure if we get to actually N95. If they would have come now, I would say, yes, we can do this. And they said it would be actually cheaper if you do something like a subscription model for filters for HVAC systems, right? So technicians come in, take the filters, bring them home, put a new one in, right? And then they clean them, bring them back in next time. So they said it would be okay for HVAC systems. We did not do a cost analysis for N95, right? But our goal was more to get rid of all the garbage that is around everywhere, right? Because if you go to a hospital setting, then you talk with the nurses and the clinicians, and they say, yeah, we use actually not just one mask per day, we can use dozens per day, right? Yes, well, sometimes they don't. They are on the parking lot outside somewhere, right? So that was also one of our goal. That's right. Good question. Yeah, thank you.
Question here.
Okay, so again, going off of the filters, are you thinking about going nationwide with this then and not just sticking with Pittsburgh once you guys have a full N95?
I mean, we want to get rich, right?
Yeah.
No, it depends on if it's really viable because the cost analysis is really the aspect that we need to think about.
Right.
But also one other aspect that I forgot to talk about is what we wanted to do is look into local decentralized manufacturing, right? Because these masks are built in a few factories around the world. And so if a hospital can have a printer like this and we give them the recipe, right, they could do this in the hospital itself. So that was one idea behind that as well. Good question. Thank you.
So I had other questions, but since we're on the filters, have you thought about, like, can you get enough pore control and phase control using like a tape caster? Because one of the advantages of binder jetting is complex structures, but also the control of pore size and pore structure.
Yeah.
So if it's not a complex shape, is this the right method?
I don't know. That's something to think about. It's a good question. Good question. Well, I think, can you have controlled atmosphere?
Well, for tape casting, you can just punch it out and you'll have little nickels and throw those in a furnace and you can do, batch processing.
Batch processing. Yeah. Could be. Good idea. Let's talk about it.
Let's do.
Other questions?
Yeah, thank you for your talk. Back to the super solidus liquid phase sintering. How does that affect the structural part performance, since that was still in the structural part section?
You need to be careful about what kind of phases you're forming, right? So potentially what you have to do is you do your densification process and then you do another process to homogenize again, right? So that could be something you need to do afterwards. But this was just about densification and repairing big defects, basically. And for that it works. But that's an excellent question. And yes, that needs to be considered for sure. So you form some detrimental phases. Yeah, absolutely. Only one per person.
Kind of while we're on forming detrimental phases, I know that for other 3D printing or AM methods like laser powder bed fusion, the alloy element composition can affect like the phases that are formed differently than with like traditional methods. Is that something that you also find with binder jet printing, or do you get around that?
So if you can get rid of the binder very cleanly, then basically what you put in is what you get out, right? Which is really nice. But the binder contains carbon and oxygen and maybe other things as well. And so if they react first with the material before you can remove the binder, then you will form oxides or carbides. And we saw this in a less controlled manner, right? When we were very early in the process, we formed carbides a lot and then oxides. That's something we always try to take care of now. Good question.
For the folks on Zoom, feel free to unmute to ask a question. And then while we'll wait, I'll follow up on that and ask, since you can control environment, have people used reactive environments?
Reactive environments, well, we used oxygen reducing environments, right? But I'm not aware of that. It could be, but that's also an interesting aspect, right? Because the post-processing really defines the microstructure, right? And properties. So using a reactive environment might be very interesting, especially for porous structures, because you can now decorate the surfaces really well with some kind of functional surface.
Yeah, or selective etching or something to remove
etching. That's great too. Yeah. Yeah. Probably ALD. Yeah.
Other questions?
I didn't say it.
RJ has a question.
Muller asked me to ask. Sorry. It's a very silly question. How far we are to get actual products from the additive manufacturing, for example, car, plane, or anything?
Oh, they are already in your plane. Every plane has additive manufactured parts in them.
Like I'm talking about the fully function. Because last year we saw a submarine got implode that used some kind of additive manufacturing.
Oh, that's not good, right? Let's not do that. No, I mean, there is rocket manufacturers that build entire rockets, including the nozzle systems now, right? And they're functional. They flew. In aircrafts, you have fuel mixing nozzles that are made additive manufacturedly from GE, for example, right? There's other parts in aircrafts that are also made via additive manufacturing. And for binder jetting, the sand casting is a super big business. So that's a part you use because you have casted structures all around you. They're probably made via sand casts that were at least developed using binder jet 3D printing. So there's many things already out there. You would be surprised. Yeah.
John.
This is more of a measurement curiosity. I'm sorry. I saw that on some of the density plots that there was the Archimedes label. So I'm assuming you were using the Archimedes method to measure these densities. I guess just from a curiosity, what does your setup look like for that? And then is there any concerns about the volume of the displaced water not hitting all of the potential pores?
Well, so you can only measure the connected pores, right? Only that. But we use vacuum in our Archimedes setup, so we're really pulling the air out. So that works pretty well. Yeah, we're doing this since a long time. We always compare to optical as well, but we use Archimedes as our standard because we trust that actually more than optical. So optical just gives you a cross section in 2D, right? And sometimes people actually, you see some publications where they take a micrograph from the center of the material, and that's their density, right? But they don't consider that the density actually varies throughout the material. That's a big issue, right? So when we do this, we always stitch the entire surface, but then you have problems with binarizing, right? Thresholding, and so that can go in all kinds of directions. So Archimedes is really our choice that we usually do, our best method. Takes a little longer.
Well, it looks like we have exhausted questions in the room, and then let's give another round of applause for Markus Chmielus.
Thank you so much for having me. Thank you.